You know, when you see an AI make the perfect move in chess or find the fastest route on your GPS, it can feel, well, kind of like magic, right? But what if I told you that underneath a ton of what we call AI, from navigation to game playing and even machine learning itself, there's one single fundamental strategy running the show? Today, we're going to pull back the curtain on that strategy. We're talking about the power of search.
All right, so let's get right into it. The key thing to understand is that pretty much any problem an AI faces can be thought of as a puzzle. I mean, think about it. You've got a starting point, a whole mess of possible moves you can make, and then, somewhere out there, a finish line, the solved state. So the big question is, how on earth does a machine find its way through that maze of possibilities to actually get to the solution?
So, here's how we're going to break it down. We'll start with a simple travel puzzle. Then, we'll look at the smart shortcuts AI uses to find the best path. After that, we'll up the ante and see what happens when the puzzle, well, fights back. From there, we'll jump into puzzles that are all about following the rules. And finally, we're going to tie it all together and see how this connects to the ultimate puzzle, learning itself.
Okay, so to really get how an AI thinks, we've got to first understand how it sees the world. And believe it or not, it all starts with something super simple: defining a goal. So let's make this real with a classic example. Picture this: you're in Arad, Romania, and you have a flight, a non-refundable one of course, leaving from Bucharest tomorrow. Suddenly, everything else just fades into the background, right? Sightseeing, finding a cool restaurant, none of it matters. Your entire world shrinks down to one single urgent goal: get to Bucharest. And that right there, that's exactly how an AI starts to tackle a problem. So here's the cool part. The AI takes our human-sized problem and translates it into a language it can actually work with. It breaks it down. Your initial state? Simple. You are in Arad. The possible actions? Well, those are just the roads you can take to the next town. The goal test is a super simple question it asks over and over. Are we in Bucharest yet? And finally, the solution. And this is important. It isn't just ending up in Bucharest. It's the whole recipe, the exact sequence of cities you drove through to get there. This formal, structured way of thinking is quite literally the foundation for all AI search.
All right, so the AI has its map. It knows where it's going. But now what? I mean, how does it decide which road to take out of town? It could just try every single road, and then every road from that town. But that would be, well, incredibly slow. There's got to be a smarter way to do this, right?
And there is. This is where the real genius comes in. It's something called a heuristic function. Now that sounds complicated, but it's really just an educated guess, a rule of thumb. It's the AI's intuition. It doesn't know the exact road distance, but it can make a pretty good estimate. For our trip, for example, it could just use the straight line distance to Bucharest, as the crow flies. It's not going to be perfect. The roads will wind and turn, but it's an incredibly powerful clue that points it in the right general direction.
And this comparison just lays it all out perfectly. A blind search is basically you wandering around, trying every single road, hoping you eventually stumble into Bucharest. It could take forever. But a heuristic search, that's like having a magic compass that is always pointing directly at your destination. You're still exploring, sure, but now you can prioritize the roads that are actually taking you closer to your goal. It makes the whole process so much faster and more efficient.
Okay, so a heuristic is like a compass for finding your way on a map. That's awesome, but what happens when the puzzle isn't a map anymore? What happens when the puzzle is an opponent who is actively trying to mess up your plans?
Yeah, now we're entering the world of what's called adversarial search. Think about a game like chess or checkers. It's not a one-way street. For every move you make, your opponent gets to make one right back. So the puzzle isn't just a static map anymore. It's this dynamic, constantly shifting battlefield where someone is literally trying to make you lose.
So how in the world do you plan for that? Well, you use a strategy called the minimax algorithm. And the logic behind it is, honestly, it's beautifully paranoid. It works by assuming your opponent is a grandmaster, an absolute genius who will always make the best possible move for them, which is, of course, the worst possible move for you. So knowing that, you look at all your options and choose the move that minimizes your maximum potential loss. It's all about picking the best of the worst-case scenarios. It's pure damage control.
And to do this, the AI has to look into the future. It builds this massive game tree of possibilities. It's literally thinking, okay, if I move my knight here, then my opponent could move their pawn here, or maybe their bishop here. If they move the pawn, then I could respond with this move, and so on and so on. Each path is a branch on the tree, and it can branch out into millions, even billions of possible futures.
Now, obviously, for a game like chess, exploring that entire tree is just impossible. It's too big. That's where this brilliant shortcut comes into play called alpha-beta pruning. It's a way for the AI to be smart about its search. It can look down one path and realize, whoa, okay, I already know this other path leads to a decent outcome for me. This new branch I'm looking at starts with a horrible move. I don't even need to see where it goes. It's a dead end, and it just snips that entire branch off the tree without wasting any more time on it.
And this shortcut, this is the secret to how AI got so good at these games. By ignoring millions of pointless calculations on those bad branches, it can focus all of its brain power on searching way, way deeper down the paths that actually look promising. It lets the AI see the consequences of a move many, many steps into the future.
And look, this isn't just some abstract theory. This is exactly the strategy that IBM's Deep Blue used to defeat the world chess champion Garry Kasparov back in 1997. And it's the same idea that allowed a program called Chinook to, get this, completely solve the game of checkers. After running for years, it proved that if both players play perfectly, every single game of checkers will end in a draw.
Okay, so we've been talking about searching for a path on a map, a path to victory in a game, but what if the puzzle is different? What if it's not about the journey from A to B, but about finding a final arrangement of things that just works, where no rules are being broken?
This brings us to a whole different kind of search, known as a constraint satisfaction problem, or CSP. The classic example is map coloring. Imagine you have to color a map of Australia. The goal isn't a sequence of steps. The goal is the finished product, a map where every region has a color, and the one big rule, no two regions that touch can have the same color, is followed everywhere.
Now, an AI doesn't see a map of Australia with its coastlines and cities. It sees something much simpler, a constraint graph. Each region, Western Australia, Queensland, etc., just becomes a dot, a node. And if two regions share a border, the AI draws a line between their dots. Just like that, the problem is transformed into a pure logic puzzle. Give each dot a color, but make sure that no two dots connected by a line have the same color.
And here's why that's so incredibly powerful. It allows the AI to use a technique called constraint propagation. Let's say it makes just one choice. It colors South Australia blue. Instantly, a chain reaction happens. The AI knows that every single one of its neighbors, all 5 of them, cannot be blue. That one decision, that single drop of blue paint, instantly eliminates a massive 87% of the possibilities for those neighboring regions. The search space just collapsed.
So we've seen how search can find a route on a map, find the winning move in a game, and solve a tricky logic puzzle. But the most mind-bending application of search is for something we almost never think of as a search problem at all. This quote really just changes how you see everything. It says, "Learning is a search through the space of possible hypotheses for one that will perform well." So think about that. When we say machine learning, what are we really saying? We're saying the machine is searching. It's sifting through this unimaginably vast space of possible ideas, of possible explanations for the world, looking for the single one that best explains the data it's been shown. Once you start looking at the world through this lens, you see search absolutely everywhere. Proving a mathematical theorem, that's just a search for the right sequence of logical steps. Creating a plan to build something, that's a search for the right sequence of actions. Even something like recognizing an object in a photo becomes a search for the right combination of patterns and features. Translating a sentence is just a search for the best possible sequence of words.
So, what's the big takeaway here? It's this: the simple act of framing a problem, defining a starting point, the possible moves, and a clear goal is one of the most powerful, most fundamental tools in the entire field of AI. It truly is the master key. It's how AI takes a messy, complicated, seemingly impossible problem and transforms it into a puzzle that it can actually solve.
And thinking about problems this way is, well, it's incredibly powerful. It really makes you wonder, doesn't it? If getting to Bucharest, winning at chess, and even the very act of learning can all be boiled down to a search problem, what else can? What other complex parts of our world are just waiting for us to define them as the right kind of puzzle? What's the next great puzzle space that AI is going to explore?